still on Laplace transform, right? In our previous class, we looked at the first theorem when it comes to Laplace transform, and we said this theorem is called what? The first shift theorem, or you call it what? Multiplying by the exponential function. We've seen how it works, right? The whole idea is that given a question, identify, is this question under the first shift theorem? If yes, then take the Laplace transform of the function multiplying the exponential function, right? Once you've found the transform, your next step is what? Identify the variable, meaning x, then add the power of your exponential. If it is negative, it becomes what? Plus. If it is plus, it becomes what? Minus, right? So that's the whole idea. Now, similarly, let's take the second theorem. This second theorem, it is called multiplying by t, or you say multiplying by t raised to the power of n. Now, just have the understanding that when you are dealing with a particular theorem, we are still referencing it to what we know, meaning the basis of Laplace transform. You know, by formula, we said what defines Laplace, or the general formula for Laplace, is that integral from the Laplace transform of what? F of t is equals to integral from 0 to infinity f of t multiplying negative st dt is equals to what? F of x. Now, what I'm trying to say is that say you are dealing with a particular theorem, say the first shift theorem, multiplying by t raised to the power of n dividing by t. All you need, you are referencing it to this very formula, which is the basis of Laplace. You know, this is what generalizes Laplace. This is what defines Laplace. So meaning that you want to understand the in-depth for a particular theorem, we call this, right? Now, the second theorem, we said it is called what? It is called multiplying by t, multiplying by t, or t raised to the power of n. You know, when we say they are actually the same thing. By t raised to the power of n, you are having what? T raised to the power of 1, which implies what? T. So we are saying multiplying by t raised to the power of n, or t, meaning it is the basis of this that we are going to use to learn this. If I'm having a transform of f of t, meaning multiplying by t, then from the result I can have t raised to the power of n, where n is what? Real number 1, 2, 3, 4, 5 likes, right? Now what we are saying is that for this particular theorem, we are saying that if the Laplace transform of f of t is equals to this, the question is, what's the Laplace transform of t multiplying f of t, right? Are you getting me? If this is the Laplace transform of f of t, then what is the Laplace transform of t multiplying f of t? Now, the idea is very simple. Now, let's write what we know. We said the Laplace transform of t multiplying f of t integral from 0 to infinity. You know, I said we are using what we know, right? In this case, do I know any formula or any integral function that defines this? Do we know it? Based on what we've done, we don't know, right? So we are now saying that let the Laplace transform of f of t multiplying t equals to what we know, right? Call this equation 1, meaning the Laplace transform of this equals to what? Equation 1. By equation 1, we are referring to the what? General formula that generalizes Laplace, or that defines Laplace. So it becomes integral from 0 to infinity f of t, right? Exponential negative st dt. You know what I have here? My answer, I would have it as what? F of x, right? But in this case, it is the Laplace transform of t multiplying f of t, not the Laplace transform of what? F of t. Meaning in this case, my result is not what? F of x. My result is not what? F of x. Now, what we are going to be doing is that we want to what we have here, say this is 2, say this is Say this is 2. Or let me bring it back to this. You know, the idea is that in this case, this is my what? This is my what? F of t, right? This is my f of t. Meaning that my f of t in this case, I must have it as what? Integral from 0 to infinity t multiplying f of t exponential negative st dt, right? Meaning this is what I must have if this is what I'm looking for the Laplace. So what we are going to do is that we are going to find a possible way to manipulate what we have. We are going to find what? A possible way to manipulate what we have. Or you say we want to squeeze it, right? So that you can get this. So I'm saying that we want to manipulate this, meaning what we have, to something of this nature, right? Are you getting me at all? Or you say you want to reduce it, or you say you want to squeeze it, or you say you want to manipulate it. So what that means is that the Laplace transform of t multiplying f of t equals to integral from 0 to infinity, right? From 0 to infinity f of t exponential negative st dt, negative st dt equals to what? F of x. Now you already understood what I'll be doing here. What I'll be doing here is that I want to manipulate this, right? I want to manipulate this, or you see, I want to reduce this so as to get this integral function, which is the expected integral function for this Laplace transform. So what I'll be doing is that, say this is the right hand side, say this is the what? Say this is the left hand side. So by doing that, I will say I have integral from 0 to infinity f of t exponential negative st dt is equals to what? F of x. Now, how to go about this is that I'm going to differentiate the left hand side and the right hand side with respect to x. I'm going to what? Differentiate the left hand side and the right hand side with respect to what? X. So I'm saying that I have d all divided by the x, all into brackets, integral from 0 to infinity f of t multiplying exponential negative st dt, close your bracket, equating it to d of the x multiplying what? F of x, right? From here we can interchange this. We can what? Interchange this. It is allowable in integration, or it's saying calculus generally. So we interchanging this, I have integral from 0 to infinity, all into bracket what? D all divided by the x f of t exponential negative st dt, equating that to d all divided by the x multiplying f of x. Now up to this level, when we say differentiate, observe your derivative. You are differentiating the function. You are differentiating this with respect to what? X. You are differentiating what you have here with respect to what? X. Meaning, I'm going to factor out other functions. Meaning, other functions will serve as what? Constant. Are you getting me? So, by doing that, I have integral from 0 to infinity. F of t is coming out. True of course. True. Right? D of t is also coming out, right? Open a bracket. D all divided by the x. D all divided by the x multiplying exponential negative st, close the bracket, right? Equating that to d all divided by the x f of x. Now let's differentiate this. What this means is that differentiate this function with respect to what? X. By the time we differentiate this with respect to x, what do you have? Let's bring it out. Let's work it out. D over the x multiplying exponential negative st. I want to differentiate this. How do I differentiate this? From differentiation, we want to differentiate this. I have let u is equals to what? Negative st, right? If u is equals to negative st, meaning I'm differentiating with respect to x, meaning that the u over the x is equals to negative t. But first thing first, what techniques of differentiation is this? Chain rule. It is chain rule. So from here, by chain rule, you know the formula, right? Meaning dy over du, dy over dx is equals to dy over du multiplying du over dx. So same idea. Now let's say this is let u equals to negative st. Say equation 1, right? From equation 1, differentiate this with respect to x. What do you have? Negative st. Negative what? St. Now from here, say this is what? Equation 2, right? Say this is equation 2. If this is equation 2, you then have, let's say initially, my function is y equals to exponential negative st. Are you getting me? So it becomes dy over d what? Over dx is equals to what? Negative. Sorry? Okay, sorry. From here, we've said let u equals to negative st. It means this same function, you can have it as this. You have the same function as, okay, from here, what it means, I have exponential always power of negative st, which implies exponential always power of u. So let's say I have y is equals to exponential always power of u. dy du, what my dy du? dy du is still exponential is power of u, right? dy du is still exponential is power of u. Therefore, the derivative of this function with respect to x is equals to dy over du multiplying what? du over dx. Input values, what do you have? You then have negative t multiplying what? Exponential always power of what? U. What's our u? Negative st. Substitute. So I'm having negative st. So you are saying that the derivative of this is what? Negative t multiplying what? Exponential negative st. So let's write that. Moving on. So we are saying that, are we together? So we are saying that the derivative of exponential, so we are saying the derivative of exponential always power of negative st with respect to x is equals to what? Negative t exponential negative st, right? Now back to what we have initially. It becomes what? Integral from 0 to infinity, right? F of t dt, right? F of t dt, all into bracket. This becomes what? Negative t exponential negative st, right? Is equals to d over dx multiplying what? F of x. Multiplying f of x. Now let's write this in a nicer way, or let's write this in a better way. So I'm having integral from 0 to infinity, minus will come out, right? So you have negative. Negative integral from 0 to infinity, f of t, right? Okay, let's put it this way. T multiplying f of t exponential negative st dt is equals to d over dx multiplying f of x. Right? Any question? Now, what we have here, say this is equation 3. Say this is equation 3. Now, go back to what we started with initially. What do I have? Integral of t multiplying f of t exponential negative s dt. And this is what? This integral function is the Laplace of what? What we have here, this is what we got now. Say this is equation 3. Now go back to what we started with. This is what we started with, right? Now what we have here, initially, we said this is the Laplace of what? Laplace transform of what? Of f of t multiplying by t. F of t multiplying by t. Now, doing comparison between these two and equation 3, what's the difference? No difference. It's just that this is positive and this is what? Negative. So you are saying that the Laplace transform of t multiplying f of t, right, is equals to what? Negative integral, right? Negative integral from 0 to infinity t multiplying f of t exponential negative st dt is equals to what? D over dx is equals to d over dx multiplying f of x, multiplying f of x. So you can, this implies that the Laplace transform of t multiplying f of t is equals to what? Negative d over dx all into bracket what? All into bracket f of x. Can you see how it works? Can you see how it works? Now from here, I'm having the Laplace transform of t multiplying f of t is equals to this integral function, right? This integral function. But this integral function is still the same thing as what? The derivative of f of x with respect to what? X. So it implies that the Laplace transform of t multiplying f of t is equals to the derivative of f of x with respect to x. Now back to this integral function. It means that the Laplace transform of t multiplying f of t is equals to what? The derivative of f of x with respect to what? X. Don't forget, you have a negative sign. So it's equals to negative d multiplying the derivative of f of x with respect is equals to negative d open bracket f of x with respect to what? X. So what this second term is telling us is that given a question, find the transform. By transform, what are we saying? F of x. By f of x, differentiate f of x. Differentiate f of x with respect to what? X. Differentiate f of x with respect to x. But in this case, we said multiplying by t or t raised to the power of n. Multiplying by t or t raised to the power of n. If the Laplace transform of t multiplying by f of t is equals to this, then t raised to the power of n becomes what? The nth derivative. If I'm having t raised to the power of 2, it means this formula, it means the Laplace transform, I will differentiate f of x twice. Just like our normal differentiation. Say you have higher derivatives, higher differentiation. By higher differentiation, we have the second order, the third order, the fourth order. Now, if this is t, meaning t raised to the power of 1, right? By t, we are saying t raised to the power of 1. So if t raised to the power of 1 is equals to single derivative, meaning you are performing your differentiation once. T raised to the power of 2 becomes what? Twice. T raised to the power of 3 becomes what? Thrice. Then up to the number of n. So generally, we can now write that the Laplace transform, of t raised to the power of n, of t multiplying f of t is equals to negative d over dx multiplying f of x, meaning the derivative of f of x with respect to x. This is the first one. The second one, you are saying the Laplace transform of t raised to the power of n multiplying f of t is equals to negative d all raised to the power of n all divided by dx all raised to the power of n multiplying f of x, meaning the nth derivative, where n is equals to real value number. If it is n raised to the power of 4, differentiate 4 times. If it is t raised to the power of 6, differentiate 6 times. So that's what the second theorem is saying. So let's take about 2 examples to see how we can solve question on this. Then we'll move on to the last theorem.